Hello students, let us discuss an important concept, parity operator and its implication for symmetric potential. So what is parity operator? To understand this, first of all, let us understand even and odd functions. So suppose if a function psi x, and if I replace this psi by minus x, it's x by minus x inversion, then if it remains psi x, then this function is called even function of function having even parity. So this is the even function of even parity. This is called function with even parity. And similarly, if I replace x with a minus x and it has become minus psi x, then this function is called with odd parity. So this is a function with odd parity. Now, what is parity operator? So when you operate a parity operator on a function x, it does the job of space inversion. So parity operator does the job of space inversion. Space inversion. So it replaces r to minus r or x to minus x. So your function becomes psi of minus x. It replaces inverts x which is a mirror image. So x become minus x. Now let me operate one more time p here. So this become p square psi x. Now if you operate p again on psi minus x, what does it will give me? It will again invert. So you'll get again, what you'll get? Again you will get psi of minus, that is psi x. So from here, I get my p square is plus minus 1. So that means if I take here, p square is 1. P square value is 1 and p value is plus minus 1. That means parity operator has an eigenvalue plus minus 1. So p has eigenvalues plus 1 and minus 1. What does this mean? So if I operate p on a psi x, I will either get plus psi x or minus psi x. That means the eigenstates of parity operator are either with even parity or odd parity. That means you can call it the eigenfunction of P are odd or even function. For example of even function, you can take uh, example is alpha x square type of functions, like a ground state of harmonic oscillator is this type of function. Or you can take first excited state of harmonic oscillator, that is say x e power minus alpha x square. This is with the odd function with the odd parity. This is a function with the even parity. If you replace x with the minus x, you'll get minus ix here. Here, if you replace psi x with minus ix, you again get the psi x only. Okay, for example, you can take say function say x square cx square. This is a function also again with a even parity. So the eigenstates of, we can write eigenstate of parity operators are with even or odd parity. Are with even or odd parity. Now, what is the implication of this parity operator on symmetric potential? So now let us write a Schrodinger equation. So if I write a Schrodinger equation, say minus time independent Schrodinger equation, this is S psi equal to E psi or simply if I write, say, Hamiltonian. So if I write the Hamiltonian, so Hamiltonian is simply minus h cut square 2m del 2 psi upon del x square plus Vx psi x at psi x. If I take as psi x here, psi x. Okay. Now I'll prove that parity operator commutes with the Hamiltonian. That is, if I take the commutator of P with H, they both commute. So I have to prove, say, P H. If I operate in function psi x, what it will give me? It will give me P of H psi x minus H P over psi x. Now, if I say the potential is symmetric. Potential symmetric means minus Vx is equal to Vx. Then what will happen? So first, let me operate P. Keep it like that. H psi x. This one I will calculate later. Let me calculate this one. H, when P operate on psi x, by definition, what I'll get? I'll get psi minus x. So this is the definition of parity operator. If you operate on x, you get psi minus x. So now this is my equation. Say this is equation number 1. Now let me take a Hamiltonian, this equation, and operate P on this equation. So if I operate P on H psi x, I'm calculating this one. Okay, I'm operating P over, say, H psi x. This term I'm calculating. What will happen? If I operate P over here, x will be replaced with minus x. So this will become minus h cut square 2m del 2. This will become minus x. And this is del x square. Similarly, Vx will be replaced minus Vx and psi will be replaced with a minus psi x. Here you have x square term, so it will again remain x square. Now, because this potential is symmetric, so what this equation suggests, this suggests me this will become h cut square 2m del 2 psi minus x del x square plus this will become Vx because symmetric, and it will remain psi minus x. So now this equation suggests me that Hamiltonian is operating on now psi minus x. Hamiltonian is operating now on this becomes psi minus x, Hamiltonian operating psi minus x. Now this is equal to this. That suggests me that my parity operator commutes with the Hamiltonian. So now whenever two operator commutes, they have a simultaneous eigenstates. That means now if I take the non-degenerate eigenstate of Hamiltonian, those eigenstate will be either with a even parity or odd parity. This the meaning of this one is because both have a simultaneous eigenstates. Now I'm talking about only non-degenerate eigenstates. So non-degenerate eigenstate of Hamiltonian will be either odd parity or even parity, because P can have only even and odd parity functions as the eigenstates. So when we'll solve the infinite symmetric infinite potential, that time we'll see the eigenstate of Hamiltonian are either odd or even function, cos or sine function only. Similarly, if you when we solve the harmonic oscillator, that time also we see the eigenstate of Hamiltonian either for harmonic oscillator, either they are even function or odd function, like e for minus alpha x square, x e for minus alpha x square. So even odd like this, they have fixed parity. So that is the use of parity operator. in explaining the eigenstate of a symmetric potential. Thank you very much.